The mixing tank problem is a really common first application for first order ODEs because it can be made without a whole lot of expertise. You don't need to know a lot of physics, and it's easy to set up, and it's also, you can use the units to try and figure out what the ODE should be. So here we go. We have this big tank, and it's there's 500 liters in the tank. We have some liquid flowing in at 10 liters per minute. We also have some liquid flowing out at 10 liters per minute. And the stuff that's flowing in, though, has 0.3 grams of salt per liter of water. So, and the other thing is the tank is full of fresh water, meaning there's no salt in the tank at time t equals 0. So you start with 500 liters of water that has 0 salt in it. You start pouring in this concentration of 0.3 grams salt per liter of water. So now the idea is write an ODE to figure out how much salt is in the tank at any time t. All right, so we're going to use Q of t for quantity. Is salt, the grams of salt in tank at time t. And so it's in units of grams. All right, next we're going to have Q prime. So the change in salt is going to equal salt coming in minus salt going out. All right, so change in salt, that sounds a lot like Q prime, and I'm going to write it as dq dt here. So we've got dq dt, and I'm going to keep track of the units at the same time as well. So dq dt is going to have, well, Q has grams, T has time, so this is in grams per minute. Right? That's going to equal salt going in. Okay, well, we can figure that out. So we have 0.3 grams of salt per liter of water, 10 liters per minute flowing in. We need to get grams per minute to have all these terms be the same, because dq dt is already grams per minute. One way we can do that is if we take the flow rate going into the tank multiplied by the concentration, we'll have liters cancel liters, and then we'll end up with just grams salt per minute. All right, so I'll write that out explicitly. We get 10 liters per minute, and we have times 0.3 grams per liter. Okay, that's salt going in. Now the next one is the hardest, so we have salt going out. So another thing about these tank problems is you assume that they're perfectly mixed. So meaning by the time the salt from this mixture falls into the tank, it is completely dispersed and there's a uniform concentration of salt throughout the entire 500 liters. All right, so that means the salt anywhere in the tank is the same as the salt at the outlet, salt concentration. So you just can take the amount of salt in the tank divided by 500. All right, so similar thing, we want to get concentration of salt. Well, that's going to be Q over 500. And now that is in grams per liter. So that's the concentration in the tank. That isn't matching the other terms. I need grams per minute. Well, this is the concentration, Q over 500. Q grams per 500 liters in the tank. We also have the flow rate coming at the outlet, which is also 10 liters per minute. So then that's going to be times 10 liters per minute of liquid. All right, so then if we cancel out all the units, right, we get liters over liters, so then we get grams per minute everywhere. So we end up with just Q prime is equal to, we have 10 times 0.3, so that's 3, then minus, we have Q times 10 over 500. Well, we can cancel some of the 10 with some of the 500, so that's going to be Q over 50. So this is a differential equation for the amount of salt that's going to be in the tank at time t. And then it's an initial value problem because the tank is full of fresh water at time t equals 0. So we also have this initial condition that Q at time 0 is 0. At 0 minutes, the start of the experiment, there are 0 grams of salt. All right, so let's go ahead and solve it. You can use separable equations, but it's a lot easier in these typically to solve with integrating factor. Let's go ahead and do that. So let's get into the right form. So we'll have q prime plus q over 50 is equal to 3. All right, so our integrating factor, mu of t equals e integral. It's already in the correct form. We have 1 times q prime. So the function multiplying q is 1 over 50. And then we have dt. All right, and that just ends up being e to the 1 over 50t. All right, so multiply the integrating factor everywhere. So we get e to the 1 over 50t times q prime plus, I'll put 1 over 50 here. Sorry, that's 15. 50 times e to the 1 over 50t times q equals 3 times e to the 1 over 50t. All right, so now we can collapse this, kind of go product rule in reverse. So we'll end up with e to the 1 over 50t q, whole thing prime, left a space for the dt there, equals left a space for the integral, 3 e to the 1 over 50t. Integrate both sides. All right, so integral derivative cancels. We get e to the 1 over 50t times q. It's going to equal, so integral of this, because of the exponent here, we have to end up multiplying by 50 to kind of cancel it out, doing the product rule in reverse. So that's going to be 3 times 50, so 150 times e to the 1 over 50t plus the constant of integration. Multiply everything by e to the negative 1 over 50t, so we'll get q of t equals 150 plus c e to the negative 1, that's correct. Negative 1 over 50 t. All right, so that's the solution to the differential equation. So now we want to figure out the c for our initial condition here, q of 0 is 0. So when t is 0, q of t is 0, so I'm going to have 0 equals 150 plus c times e to the negative 1 over 50 times 0. Well, that ends up being e to the 0. E to the 0 is 1, so we have 0 equals 150 plus c. So that means c is equal to negative 150. The solution is q of t equals 150 minus 150 e to the negative 1 over 50t. All right, and it turns out this does make sense. So if t goes to infinity, this whole term disappears. This 150, it should be the amount of salt that's in the tank if you just run t to infinity here. And that does make sense. So if you have this amount of salt flowing into the tank all the time, then you'd think eventually the amount of salt in the tank is going to go towards the concentration of salt that's falling in, right? So what if we had 0.3 grams of salt per liter of water in a 500 liter tank? All right, so 0.3 grams salt per liter times a 500 liter tank. So that's 3/10. So it's 3 over 10 times 500. That ends up being 150 grams of salt. All right, so just do that one more time, right? The limiting concentration of the salt in the tank, the salt in the tank, the water in the tank, the liquid in the tank should eventually have pretty much the exact same concentration of the salt water flowing in, right? Over time, you kind of replace it over and over again. You have to wait till infinity to do it, but that's what's going to happen. You'll get the concentration coming in will be approximately the concentration in the tank. So, right, so then we have the concentration of the stuff flowing in is 0.3 grams salt per liter water multiplied by 500 liters in the tank to get the total amount of salt in the tank at infinity, and you get 150 grams of salt in the tank as t goes to infinity.